Okay, welcome everybody. So, standard apology for not putting out videos as much as I'd like to, but I am doing this on the weekend because that's how much I want to make a new video here, and obviously want to keep growing the channel, so I need to keep putting out content. So, I've been working on this for a few days now, actually, and we're going to talk about quantitative EDS in the STEM today. Okay, so I'm sure the majority of you are familiar with EDS, but this is, those of you who are not, this is where you are using characteristic X-rays generated from the sample as a result of inelastic scattering for chemical analysis to figure out what elements you have present. And so specifically, we're going to talk about how to use that information to quantify the composition of your specimen. Okay, so we have an example here on the title slide of an EDS spectrum. Okay, and so some of these peaks correspond to certain elements, and we want to be able to use this to figure out how much of each element we have. Okay, so that's what we're going to go over today, is the ins and outs of this and how this works. Okay, all right, so okay, so I'm going to hit you with some math first. Okay, because this is really the heart of how this works. And I want to stress that the math we're going to go over today, this is unique to EDS in the STEM. Okay, you cannot apply this to, say, the SEM. I want to make that very clear because of the nature of your samples in STEM, as well as the electron energies that you're using in STEM. Okay, but basically, right over here, right in the upper upper left here, is we have this standard equation, which is called the Cliff-Lorimer equation, which basically says that my atomic fraction ratio of two elements is equal to the ratio of the net counts of element A divided by the net counts of element B multiplied by a sensitivity factor, KAB. Okay, and this is the Cliff-Lorimer equation. Okay, so we're going to go over what all of this means here in a minute, specifically what net counts means, right? But before we get to that, if you take this sensitivity factor and you actually decompose it, okay, so you have a component related to element A, right? And that is the denominator here that the the counts for element A is being divided by, and you have a similar term here for element B, okay? And this is what composes the sensitivity factor, right? So if you do a little math, you end up with this over on the right, okay? So I've separated this out into basically two parts here. So the part on the left, sigma A, omega, and epsilon, and then to the right of that, you have ACF, okay? So the ACF term, just going to briefly go over this here, is related to absorption of the X-rays in the sample. We call it the absorption correction factor, ACF, okay? This is something that can be important, certainly, when you're doing quantification, but it's difficult to accurately account for it when we're doing quantitative analysis, okay? So part of the reason for that is, in order to accurately model the ACF, we have to actually know what the sample composition is to begin with. And that's a bit of a problem because we're trying to actually measure that in the first place. So you end up with this kind of circuitous chicken and egg sort of logic here, where you don't know what the composition is, but you need to know it in order to, account for absorption. So so it can be important, certainly. If you have a thinner sample, it tends to be less of an issue, okay? But for our purposes, we're actually going to just neglect this for the time being and assume that we don't have an absorption correction factor. Okay? And we're just going to concentrate on omega A, sigma A, omega, and epsilon, okay? So again, quantitative, we want to know the amounts of the elements that are present. In a qualitative sense, we're just interested in knowing what elements are present, okay? That's pretty easy. You're just looking at peaks in the spectrum, okay? So again, difficult to account for absorption, so we're going to neglect that here. If we do that, so we just remove those terms, okay? So what we can do then is we can define a new set of a new set of terms called corrected counts, okay? So basically that's just the net counts divided by that sigma A omega epsilon term, okay, for each of the atoms, okay? So now you have the ratio of your atomic fractions is equal to the ratio of your corrected counts of A by your corrected counts of B, okay? And now your sensitivity factor just has the sigma A omega epsilon terms in it, okay? The other way you could rewrite this, if you wanted to know the absolute instead of just the relative atomic fraction, right, is you take the corrected counts of A divided by the sum of the corrected counts of A plus B, okay? So the question then is, how do we do this? Well, we can figure out the sensitivity factor experimentally if we have a known standard sample, okay? Meaning we know what the composition is, okay? But it's not always the case where we have the luxury of doing something like that, okay? So especially if you're dealing with kind of a more exotic material or something that's not very commonly used, right? It may be difficult to find a standard that can work for what you're trying to do, okay? So what we're going to talk about today is how to actually calculate the sensitivity factor from first principles using known data about the elements and known data about your EDS detector, okay? So that's what we're going to do today is we're going to go over how to do quantitative EDS from first principles without having any standards, okay? All right. So one of the kind of, shouldn't say controversy, but there is kind of some discrepancy as to what the convention is. Do I use atomic fraction or do I use weight percent? So as I have written it, you have atomic fraction is equal to the ratio of the corrected counts to the sum of the corrected counts. If you want to convert this, your atomic fraction to weight fraction, right? You can just use this equation here, okay? So you're just multiplying your A atomic fraction by the atomic mass of A, and you're dividing by the sum of the products of the atomic mass and weight fractions for the other two components, okay? So if you wanted to rewrite the equation for the weight fraction, okay, so if you wanted to rewrite this right here, okay, and do it in terms of weight fraction, okay, you end up with this. So basically now, right, you have the atomic fraction of A divided by B absorbed into your K factor, okay? And that would be a perfectly valid way to do this as well. That would just be something you'd have to keep in mind. What you're getting then is weight fraction ratio, okay? So there isn't really a clear consensus on which of these is correct. Okay, they're both correct mathematically. You just have to make sure you know which one you're doing. I personally prefer to use atomic fraction. I think it's just more intuitive. So if you use an interesting example like indium phosphide, okay? Indium has a much higher atomic mass than the phosphorus, but it's intuitive, right, that I have a 1-to-1 atomic fraction ratio. But if I look at this in terms of weight fraction, I end up with something a little bit less intuitive, right? So it's almost, you know, a weight fraction ratio of 4, okay? So this is why I tend to prefer atomic fraction when I'm doing my quantification, but you could use this information to go to weight fraction if you wanted to. Okay, so if we wanted to generalize this for n elements, because, right, what I've shown you to this point is just 2, okay? So it's pretty simple, right? So your atomic fraction for element I is equal to your corrected counts divided by the sum of all your corrected counts of all the elements present, okay? And then if I want to convert that to a weight fraction, I just do the atomic mass of element I times the atomic fraction of element I divided by the sum of the products of the atomic mass with the atomic fraction of all the elements present in the quantification, okay? That being said, right, the relative equations for atomic mass or for atomic fraction and mass fractions are still valid. So this equation would still be valid right here for the weight fraction, okay, as would this equation for the atomic fraction, okay? Those are the same regardless of how many elements you have present. Okay, so we introduced this idea of a net counts when we're doing quantification, okay? So the idea behind a net counts and a net spectrum is that we have the spectrum that we have as collected, okay? What we have to do is we have to subtract the background contribution from that spectrum. So the background that we get in the spectrum is due to two sources, right? You have detector noise and you have continuum X-ray generation, meaning X-rays that are not characteristic X-rays. So those add up together to give us a background, okay? And those are not related to the elements present, okay, in terms of providing quantitative information. So we have to remove that from the as collected spectrum, and then we get a net spectrum, okay? So then as far as what I sub A net means in the equation, this is the total counts in the peak between the full width half max in the net spectrum, okay? And we're gonna go over what this looks like here in a minute, okay? So some things we can consider here, right? Our ideal situation is where we have peaks that are nicely separated, but we can also look at what happens if maybe we don't have that, right? What happens if we have maybe, you know, peaks that kind of overlap? In that case, the way we deal with that is we use some math, okay? So we have to do some curve fitting by using Gaussian profiles. And then once we have a Gaussian profile that models our peak of interest, we can then use that to figure out the net counts associated with that peak, okay? Okay, so here's an easy example or an ideal example, right? So we have on the left, this is the cerium L X-ray family, and this big peak right here, this is the L alpha peak, right? So you can see your red line is the as collected spectrum, and the green line is the background, okay? So if we subtract the spectrum from the background, we end up with what you see on the right, okay? So you can tell when the background subtraction is good, because basically you should be going all the way down to 0 here, right? So, right, you remove the background and you're starting at 0, as you would expect, okay? If we had the background still in here, then we would have a bump up in this, but we don't, so this is perfect, okay? So then this is your peak intensity of the net spectrum, right? And then you have the full width half max on the left and on the right. So at each energy or each what we call channel in the X-ray spectrum, we have a number of counts, right? So that's why I plotted this as a bar graph, okay? Because so each of these has a number of counts. So basically all we have to do is sum up each of these values under the peak, and that gets us our net counts for the peak, okay? So mathematically, it's, you know, not terribly involved to compute the compute the net counts for an idealized sample like this, okay? But let's consider what happens if we have maybe something less idealized. So we have molybdenum now on the left, and this is again the L X-ray family, but unlike the case of the cerium, we now have the L peak, which is overlapping the L alpha peak, which is overlapping with the L beta peak, okay? So that means that this peak on the left is no longer just a contribution from L alpha. It has a, you know, some contribution from the beta peak. So we have to deconvolute those, okay? So what we do is we take the net spectrum data, and again, you see, right, I have the background component here, okay? So we take the net spectrum data and we can fit a Gaussian profile. Actually, I should say two Gaussian profiles, right? Because we have two peaks here. I'm only showing the one associated with the alpha peak, okay? But once we have the one associated with the alpha peak, it's the same idea, right? So we can figure out the full width half max, and we just compute the area under the curve, basically, right? Between the full width half max, okay, from left to right. And then we can use that for our I net for that element, okay? So we have a little more work to do if you have some peak overlaps, but something that can still be done fairly easily if you have the ability to model it. I did this actually with Kaleidograph. MATLAB does have the ability to do Gaussian peak fitting, but I don't have that feature actually in my version of it, so I had to use Kaleidograph, which does it pretty well actually. Okay, so another question we can ask is, when we see these peaks in the spectrum, are they actually statistically significant? Okay, so we have an example here of a not statistically significant peak. So there's actually an easy equation that describes this, which is right here. So if you take your net counts, right, so your counts where you have the background removed, that needs to be greater than 3 times square root of the background over the same window. Okay, so if you look at the example on the right here for the calcium K alpha peak, okay, you can do the math. If you want, you can find out that you do not meet this criterion, right? So you don't have a statistically significant peak, which makes a lot of sense, right? Because you can see that I barely have any kind of signal that's above the background level here, okay? So the point of this, right, is that if you have a peak like this, you should actually ignore it, okay? Both in a qualitative and also a quantitative sense, right? So you can't put something like this in your quant to try and figure out, you know, how much of element X do I have, okay? Because you don't have statistical significance. Here's an example, of course, of a peak that is statistically significant, right? You can see very obviously, okay? You don't have to do the math. This is very obvious. So my net spectrum is outweighing the background by quite a bit, just in terms of the raw area, okay? So this is very obviously a statistically significant peak, okay? But you can't always tell just by looking, right? So you do have to do the math to see if you actually meet this criterion. Okay, so now that we've discussed what net counts means, we can get into the guts of the sensitivity factor, right? Which are these 4 parameters: sigma, A, omega, and epsilon, okay? So these refer to the ionization cross-section, the electron transition probability, the fluorescence yield, and the EDS detector efficiency, okay? And again, I have my sensitivity factor, if I'm looking at the ratio of element A to B, is the ratio of 2 products of sigma A, omega, and epsilon, okay? So these factors are all unique to the atoms that I have present, okay? The relevant subshells of the atoms, as we're going to see, the X-ray energy that is emitted, and also the construction and properties of my EDS detector. Okay, so we're going to start in order here. So the first thing we're going to talk about is the ionization cross-section. So in order for an X-ray to be generated, you have to have what's called core shell ionization. Okay, so we're going to see an example of this here in the next slide. And so we use sigma to indicate how readily this happens. It does have units of area, and the units that we usually use for this are called barns, okay, which is kind of funny because the actual area corresponding to a barn is really, really small. Okay, so you can see 1 barn is equal to 10 to the minus 28 square meters, or 100 femtometers, right? You don't often use the units of femtometers, but here's one example where you actually could, right? 1 barn is equal to 100 femtometers, okay? So on the order of the area, cross-sectional area of an atom, okay? But you don't want to think of this as a physical area. You want to think of this more as a probability. So as my cross-section gets bigger, what that means is it's easier to ionize the shell, okay? As it gets smaller, it means it's more difficult to ionize the shell. It is a strong function of electron energy, as we're going to see, and it is unique to the shell for the atom in question, okay? So the atoms all have, different shells, and the cross-section to ionize each of them is different. Okay, so the core shells we can denote as K, L, M, and then I didn't list N, but you could. And then from L on up, you actually have subshells. Okay, so in the case of L, you have 1, 2, 3, and then in M, you have 1, 2, 3, 4, 5. And so this obviously depends on what elements you have present. So not every element, for instance, is going to have M subshells, right? You gain more subshells as your Z gets bigger, okay? So just to schematically show how this works, right? So if we're looking at, say, K alpha, K beta, L alpha, and L beta X-ray generation. So on the left, we have the K alpha and beta emission. So we start by ionizing the K shell, right? So electron comes in, knocks out an electron, and then if an L shell electron transitions down to the K shell, I get out a K alpha X-ray, okay? If I get a transition from the M shell to the K shell, that's a beta X-ray, okay? Same idea holds for L alpha and L beta, except now I'm ionizing the L shell. So I ionize the L shell, I get a transition from M to L, okay, to fill in the empty state, and I get out an L alpha X-ray, or I could go from the N to the L, and now I have an L beta X-ray, okay? Overwhelmingly, the alpha peaks are preferred for quantification. The main reason why is that they tend to be the most intense. Well, they pretty much always are the most intense. Okay, so pretty much always you're going to be using the alpha peaks when you're doing a quant. Okay, although if you wanted to, technically, you could do the quant with, say, a beta peak if you wanted to for some reason. Maybe you have a really bad overlap or some sort of extenuating circumstance. You could use a beta peak, but the vast majority of the time, you would be doing quant with an alpha peak. Okay, so the question then here, right? So we have X-ray peaks, we have core shells, and we have this ionization cross-section, okay? So again, we prefer the alpha peaks for doing quantification. If you can, you usually prefer to use the K alpha peak. But you don't always have the ability to do that, particularly as your elements get higher in Z. As we're going to see, it becomes harder to detect the K alpha X-rays. So then usually you are forced by necessity to start using the L and sometimes the M X-rays, okay? So for a K alpha X-ray, you're getting the K shell ionized, okay? For the L alpha X-ray, you're getting the L3 subshell ionized. Notice for the K, I didn't write subshell because there are no K subshells. There's only one shell, okay? But for the L, you now have 3 subshells. And then for the M alpha, you would be getting ionization of the M5 subshell, okay? And then, of course, the other part of this is that you have an energy dependence. So we're going to actually see now some data on this. So there's a great program by NIST that calculates your ionization cross sections. Okay, I will put a link in the description box so you can access this and download it. It's free. It's very easy to use. Okay, so this is the sigma data for silicon. Okay, so you can see we only have 3 shells to consider, right? K up through L3. Okay, so you can see that as I go from K to L, my cross section gets bigger. Okay, so the K shell is always the most difficult to ionize, right? Which makes sense because that is the most tightly bound and close to the nucleus. So as I move away from the nucleus, it's easier to ionize the shell. Okay, so the cross section gets bigger. Okay, so as I'm going from top to bottom, I'm decreasing in my ionization probability. Okay, you can also see the energy dependence as I go from left to right here. So you can see that below a certain energy, I'm not getting any cross-section value, okay? So there is a threshold energy to cause ionization, right? Which makes sense because you have an ionization energy for the shell. You tend to get a bump here, and then it kind of levels off, and then it actually kind of bumps up a little bit as you go along here, okay? So you do have an energy dependence. So you can pump in 2E5 here for 200 kilovolts, and you can get the values here, okay? So again, I have the values here listed for units of barns, okay? If we look at a higher Z element, right, gold now, so now I have more subshells because I have a higher Z element, okay? But the same idea holds here, okay? As I go from L out to M, my cross-section gets bigger, so it's easier to ionize, okay? So again, as I'm going from top to bottom, my ionization probability is decreasing, okay? Okay, so how does sigma factor in to the quantification? Well, what we saw is that the corrected counts is proportional to the net counts divided by sigma, okay? So if I have a small ionization cross-section, that means that the value for the net counts that I measure will tend to be lower than expected. So by dividing by the cross-section, that boosts the corrected counts and accounts for that issue, okay? And then by extension, right, if I have a large cross-section, I'm going to tend to measure a net counts that's kind of larger than expected. So dividing through by sigma will decrease the corrected counts and again, helps to account for it. Okay, so the next thing is the transition probability. So after I ionize the core shell, I then have several different transitions that may happen to fill that empty state, okay? And each of these transitions has a probability, okay? So my transition probability goes from 0 to 1, right? Because your probability can't go outside of those bounds, okay? But which transitions actually happen have to conform to what's called the dipole selection rules, okay? So if you think back to your quantum numbers, right? One of your quantum numbers for your electrons is L, the azimuthal quantum number, okay? So one of the rules states that when you have a transition between states in the atom, you have to have a delta L of plus or minus 1, okay? So another way to think of this, right, is you have SPDF, right? So L equals 0 for S, L equals 1 for P, L equals 2 for D, and so on and so forth, okay? So I could have a transition from a P state to an S state, right? Because that's a delta L of 1, okay? Absolute value, right? I could not, though, have a transition from a D state to an S state because that would be a delta L of 2 absolute value, okay? The second rule concerns J. So J is the sum of L and S. J is the total angular momentum. So that is the sum of the azimuthal quantum number and the spin quantum number, okay? So I have to have J, the delta J equal to 0 or the delta J equal to plus or minus 1. Okay, so what this means then, as far as like K transitions, for example, I could go from L2 to K or L3 to K. Those would both be allowed, okay? Because the L2 and the L3 shells would have the J that conforms to this, okay, without going into the detail here. I could do a whole presentation about, you know, what the different subshells is, right? But I don't want to bog you down with this. But forbidden, for instance, right, would be something like L1 to K, okay? So I'm going from the L1 to the K shell. This is a delta L of 0. And if I did, for instance, M5 to L2, right, because you ionize this state and you come from the higher state, right? That would be a delta J of 2, so that would not be allowed, okay? All right, so again, if we look at some examples of this, right, let's look at silicon again, just as an example. So there's 5 possible transitions here, okay, once I have K-shell ionization. So I can go from L3 L2, L1 is listed, although technically this should be 0, and it basically is, right? Because this should be forbidden because I'm going from an S state to an S state, okay? So effectively it's listed as 0, okay? And then I have M3 and M2 to K, okay? So now where I got this data, there's a great website that actually has tabulated X-ray data. I will again put a link in the description so you can find this yourself, okay? So the two transitions that make up the alpha peak are, right, K to L3 and K to L2, okay? So I sum those two relative intensities together, okay? So 0.59 plus 0.3, and then I divide that by the sum of all, I divide that by the sum of all of these, okay? So if I do that, I end up with about 0.9. Okay, and generally speaking, you have a K alpha transition probability of about 0.9 pretty much consistently for all the elements, but there is a little bit of variation from element to element, okay? So this is, strictly speaking, unique to the element in question. For some elements, your transition probability for K alpha will be 1, okay? So the lower Z elements at some point don't even make a beta peak. Okay, if they don't make a beta peak, then all you have is alpha. Your transition probability is 1. Okay, I'm not sure the Z at which that happens. I think it's around Z12. So if you're below, I think it's 12 or 11, somewhere in there, you only have K alpha X-rays. Okay, so your transition probability would be 1 in that case. If we look at cerium, right, this gets a little more complicated, okay? So we're looking at the L alpha transition probability. So we have a bunch of different L X-rays here that can come out of cerium, but this is actually not too difficult here because we're only interested in the transitions where you're starting with the L3 shell being ionized, okay? So that's only the ones indicated by the arrow, okay? And the ones that make up the alpha peak are the first two, okay, at the top, okay, the L3 to M5 and the L3 to M4 transition. So again, we do the same math and we end up with a transition probability of 0.81, okay? Again, this is unique to cerium. There's definitely more variability with the L alpha transition probability from element to element than you would get with the K alpha versus K beta, okay? And again, you only get L alpha X-rays and L beta X-rays once you get to a Z that is high enough. I don't know what that is exactly, but this is limited to heavier elements per se, okay? All right, so now that we've seen how we get A here, okay, the transition probability, how does this factor into the quant? Well, again, we take the net counts and divide it by A, right? That factors into getting the corrected counts. So if I have an A that's really small, right, I'm going to tend to have a reduced net counts. So by dividing through by A, that increases my corrected counts, okay? So then as I approach 1, right, I'm going to end up with a net counts that really is not affected by the transition probability. And so then I don't really get an effect on the corrected counts, okay? All right, so moving on. Next factor is the fluorescence yield, okay? So again, we have core shell ionization. We now have a probability that ionization results in X-ray emission. And this is what we call the fluorescence yield, okay? So again, this goes from 0 to 1. This is independent of the beam voltage. So this is different than the ionization cross-section. It does have dependence on the shell. So your K shell has the highest yield, followed by L and then M. It also increases with Z. So your heavier elements tend to have higher fluorescence yields, okay? And then as a complement to the fluorescence yield, we can take 1 minus omega and we get something called an Auger yield, which we'll get into here in a second, okay? So here's some data on this, okay? And again, so the table on the right is from a great publication that has a list of all the tabulated fluorescence yield data on a tremendous number of elements. And again, I will put a link in the description so you can see it, okay? But you see graphically on the left, right, as I go from, the lower Z to the higher Z, right, I have a fluorescence yield that goes up and tends to approach 1. And then I see the same trend with L, but you can see the L yield is much lower than the K yield. So just using something like carbon as an example, carbon has a fluorescence yield of about 1/1000. Okay, so that means I have to cause 1,000 core shell ionizations to get 1 carbon K alpha X-ray out. Okay, so you can see, right, the lighter elements are less efficiently detected in terms of or less efficient in terms of their X-ray generation than the heavier ones are. Okay, versus something, that's here around like 0.5, right? Which would actually correspond to something like germanium, right? So I have a fluorescence yield that's now about 50%. Okay, so 50% of the time I'm getting out an X-ray. Okay, you can see the same basic trend as I go from lower Z to higher Z, right? My fluorescence yield for the K shell tends to go up. Okay, with the L shell, what's interesting is there's actually some holes in the data, okay, where there actually isn't published data available. Okay, so they actually left those spots blank here in the table. Okay, but you can see the general trend here, right, is that I'm increasing the value as I go up in Z. Okay, you should also note that for L, because you have 3 subshells, this is actually an averaged value. Okay, this is not specific to any of the subshells, but with the K shell, you only have 1 shell. Okay, so if we're not getting out X-rays all the time, what's happening? Well, the other thing that's happening is we're getting out Auger electrons. Okay, so on the left, we saw this example of the L alpha and L beta X-ray generation, right, where we ionize the L shell, we get a transition from the M or the N shell, and we get an L alpha or an L beta X-ray out. Well, that doesn't always happen, okay? So what could happen is after I generate this X-ray, okay, the X-ray still has to escape the atom, okay? And what can happen is it can be absorbed or transfer all of its energy to another core shell electron, okay? And if it does that, the X-ray is not going to be emitted, right? You're going to get an electron emitted instead of an X-ray, and this is what's called an Auger electron, okay? And this Auger electron, like the X-ray, has characteristic energy. So you can actually use Auger electrons to do chemical analysis, similarly to how you do X-rays for chemical analysis. It's a little bit different with Auger electrons because it tends to be a far more surface sensitive issue, right? You're not doing Auger inside of a TEM per se. You actually have special instrumentation specifically designed for doing Auger electron detection, okay? And again, the Auger process tends to be preferred, right, with the lower Z elements, okay? And it tends to be preferred with the L and the M shells as opposed to the K shell, okay? All right, so again, we want to relate omega to the quantification, right? So again, we're dividing the net counts by omega. So if I have a small value of omega, that's going to mean that my net counts will tend to be reduced. So if I divide through by omega, that boosts my corrected counts, okay? And then as I approach 1, right, I don't really see any change, okay? So that's why we divide through by omega, okay, to get us the corrected counts. All right, and then the last factor is the EDS detector efficiency. Okay, so EDS detectors do not detect all X-rays with equal efficiency. Okay, so there's what's called an efficiency curve for each detector, and this is a strong function of your X-ray energies. So what we're going to see is there's actually kind of a sweet spot in the efficiency curve, and the very low and very high energy X-rays tend to be most affected. Okay, although there has been some improvement in recent years with lower energy X-rays being more effectively detected. So just like omega and A, epsilon is a pure number. It goes from 0 to 1. Okay, so we can look at some example curves here. Okay, so this is taken from the a application note, I should say, for the what's it called? Application note for the Super X detector on the Thermo Fisher Themis. Okay, well, it's not specifically limited to the Themis, but anyways, I'll put a link again to the description so you can find this yourself. Okay, but they have actually two examples here of two efficiency curves. Okay, so they have one that has a window and one that does not have a window. Okay, so the basic idea here is as I go from lower energy X-rays to higher energy X-rays. Keep in mind, this is a logarithmic scale. So this is 100 electron volts. This is 1 kilovolt or keV. And then this is 10 keV. And then this is 60 keV. Okay. So we can see that my efficiency is not so good down here. And then it bumps up actually pretty rapidly. And then by the time I get to around 1, I have very high efficiency. And basically from 1 to 10, I have a very high efficiency. And then I get this drop off here. Okay, so why does this happen? Maybe before we discuss that, let's look at the blue curve, right? So this is what happens when we put what's called a window in front of the detector. Okay, so we put a window in front of the detector, I get basically a pretty substantial drop in all of the efficiency values. Okay, so this is why now pretty much all of the EDS detectors that are being made are windowless. Okay, the reason that detectors had windows for the longest time was to prevent contamination from getting on the detectors. But because the vacuum systems and the TEMs are so good now, they're basically irrelevant and unneeded. Okay, so we don't make detectors that have windows anymore. Okay, and you can see the result of doing that is we get a lot better performance out of the detector. Okay, but anyway, so why does this happen here? Okay, so you have, based on the construction of your detector, right? You have different layers, you have contacts, you may have a window if you have an older detector. Okay, and all of those things your X-rays have to pass through in order to get detected by the active area of the detector. Okay, so part of your inefficiency here, right, at the lower energy X-rays is you have things like contact layers that your X-rays have to go through. Okay, as your X-ray energy gets higher, it becomes easier to penetrate through those and then go into the active area. Okay, but then you might be wondering, well, why do I get this drop off when I get to 10? Right? Why does this drop off and then down at 60 keV, I once again have pretty poor efficiency? Well, as your X-ray energy goes up, it actually becomes possible for the X-ray to just pass straight through the detector without being detected. Okay, so your active area has a finite thickness, right? And if it's not thick enough to prevent that X-ray from passing through it, right, it will just go through it and you won't detect it, right? So that's why you see this drop off here at the higher X-rays, right? Is the X-rays just have so much energy that they just pass through the detector. Okay. Okay, so you can see though, like primarily, if we were to look at something like oxygen, right? Oxygen has an energy right around here. You can see the benefit that we got from getting rid of the window, right? So we're almost at 90% efficiency now versus what we had previously, which was around 30% efficiency with a window. Okay. Okay, so once again, how does this relate to the quant? Well, if I have an X-ray where the detector efficiency is not so good, right, that's going to tend to reduce the net counts that I measure. Okay, so if I divide through by my efficiency, that ends up boosting the corrected counts. Okay, same idea happens as I approach 1, right? I don't really have an effect at that point, okay, because my efficiency is good, so my net counts tends to be more representative of what I should be measuring. Okay, so I'm not going to end up affecting the corrected counts in that scenario. Okay, all right. So we've gone through all 4 of those parameters, right? Sigma, A, omega, and epsilon. one of the questions that comes up a lot is how accurate is your quantification, right? So this gets us into uncertainty analysis, okay? So which I'm going to go over, briefly here in just a couple slides, okay? So the first thing to keep in mind is that your uncertainty is always improved as you collect more counts, okay? The more counts you can collect, the better your quantification uncertainty will be, okay? You also have to keep in mind things like how well you're removing the background, right? You want to make sure you're doing that accurately, okay? Particularly if your peak is not a very strong one, right? If you have the issue of peaks that are overlapping, right? How well are you deconvoluting those peaks, okay? So you want to make sure your math is good, right? You also have to keep in mind that we are calculating the sensitivity factor theoretically from first principle, okay? So in that scenario, the primary source of uncertainty is the uncertainty in the sensitivity factor, right? You can calculate the sensitivity factors experimentally using a standard, and in that case, you will have a reduced uncertainty in the sensitivity factors, but that's not what we're doing here, right? We're talking about how to do this from first principles when you don't have the ability to use a standard, okay? So we can look at some very simple equations here to kind of give you an idea about what kind of uncertainty we're dealing with, okay? So this is the equation that tells us the uncertainty in the ratio, or I should say the relative uncertainty in the ratio. Okay, so delta meaning the uncertainty in the ratio divided by the ratio. Okay, so I have three terms here underneath the radical. I have one for the relative uncertainty of the sensitivity factor, and then I have two that are related to the net counts in the peak for element A and element B, okay? So let's just assume for the moment, right, that we're not worrying about the uncertainty in the sensitivity factor, okay? So let's just neglect this term, and we'll only worry about the terms related to the net counts, okay? So if we do the math here, let's say we have 1,000 net counts in each peak. That ends up giving us a relative uncertainty in the ratio of 13.4%. Okay. If I go to 100,000 in the B peak, my uncertainty drops to just under 10. If I go to 100,000 in both, I'm down to 1.3%. And then if I have 1,000,000 in both, I'm under 0.5%. Okay. So the moral of the story here is the more counts you have in the peak, the better in terms of your uncertainty, okay? At least your uncertainty that is related to the counts that you are collecting, okay? Again, we're not worrying about the uncertainty in the sensitivity factors here, okay? But we're going to do that next, okay? So if we want to consider the uncertainty now in the K factor, we can look at the uncertainty in the product of our sigma A omega epsilon values, okay? So again, we have a relative uncertainty here, okay? So we have relative uncertainty in sigma, relative uncertainty in A, relative uncertainty in omega, and relative uncertainty in epsilon that we are adding in quadrature, okay? And so, certainly, right, no pun intended, we don't know all of these to a high degree of accuracy, okay? So probably the term here that has the most uncertainty is the scattering cross-section, or the ionization cross-section, I should say, because those are being calculated theoretically from first principles. Very difficult to actually measure those experimentally, okay? The transition probabilities, those are known to a little bit higher accuracy, right? Because those are based on experimental X-ray data, okay? The fluorescence yield data as well. So those are measured experimentally, but again, you do have uncertainty with those as well. And then the last one, you have the uncertainty related to your detector, okay? And, again, those curves are calculated theoretically. They're not usually measured experimentally, okay? Difficult to do that. So, I mean, you really, when you look at this, you do have reasonably sources of uncertainty with all of these things, okay? But let's look at some of the math here. So let's assume that we have 2% uncertainty in just two of these terms, okay? That gives us a total uncertainty in, or relative uncertainty in my product there of about 3%, okay? If it's all the terms, it goes to 4. If it's 5% uncertainty in half of the terms, it's a little bit over 7. And then if it's all the terms, it's 10%, okay? So the point here, though, is that this is the main source of error in my quantification uncertainty when I am doing this without a standard, okay? So you have to keep that in mind, right? Is you're calculating these values theoretically, some of them anyways, okay? And so you have to account for that when you are doing this. So uncertainty of 5% in each of those is not unreasonable, I would say, which would give you an uncertainty overall of about 10%, again, in your sigma A omega epsilon product, okay? All right, so just to put it all together for you, right? So we started with this equation, the Cliff-Lorimer equation. The ratio of my atomic fractions is equal to the sensitivity factor times the net counts of A divided by the net counts of B, okay? And we showed what was in this sensitivity factor, which is a product of 4 subcomponents, right? Sigma A, omega, and epsilon, okay? We also introduced this idea of corrected counts, right? If I take my net counts and divide through by that product for each of the elements, right? I end up with a corrected counts, and then my ratio is equal to the ratio of the corrected counts of A divided by the corrected counts of B, okay? Again, you could generalize this, right, to any number of elements, okay? So then again, you have the corrected counts of A divided by the sum of the corrected counts. And then if I had, say, CD, right, I would just add that in here under in the denominator, I should say, okay? So, but this is a rigorous, what I call clear box approach to doing quantitative STEM, STEM-EDS, okay? This isn't like when you punch in numbers into software and you're just getting a result out, okay? You know what's going into it, right? What's going on, how the math works, what the values are, okay? This is much different than like the black box calculations where you're just, you know, you're saying, okay, here's a spectrum, give me an answer, right? That's a black box calculation. And I would always be very cautious when you use those, okay? Because you don't know what's going into it and you don't know what is included in that, okay? Of course, right, we showed that there's some uncertainty, right, in these measurements, okay? I don't think something on the order of 10% is unreasonable when you're talking about a standardless analysis like we were doing here, where we calculated the sensitivity factors from first principle, okay? The other thing, too, of course, is that we neglected absorption in this, right? Because it's difficult to model, but there would also be that you would need to, you know, possibly take with a grain of salt, okay? So with that, right, now get out there and do your own quantification, right? I know it seems kind of daunting, but it's really not. You know, you can just do a little math and a little bit of processing of data, and you can do this yourself. And then you don't have to rely on black box calculations. Again, I'll put all the links in the description box so you can see where I'm getting the data that I'm using if you want to do this yourself. So if you have any questions, please let me know, and look forward to doing more videos soon. All right. Thank you, everybody.